Hello, my name is Sihui. I'm a PhD student from Colorado School of Mines. Here I'll present our paper, Sample-Driven Connectivity Learning for Motion Planning in Narrow Passages. Let's start with the motivation. Motion planning finds a path connecting the start to the goal. Sampling-based motion planning solves the problem by sampling in the configuration space and connecting the samples. They are very efficient in covering large open spaces, but does not work well when there are narrow passages, especially in high-dimensional configuration space, since the probability of sampling in these narrow passages is very low. In this paper, we introduce an algorithm called Sample-Driven Connectivity Learning, or SDCL, which learns from existing configuration space samples to guide new sampling through narrow passages. This algorithm runs in parallel with a probabilistic roadmap, or PRM, and it has two main steps: learning a manifold and sampling the manifold. Next, we'll discuss the algorithm steps in detail with a 2D example. We have this 2D configuration space where the blue region is the obstacle region. We want to plan a path from the start to the goal, but there is a long, narrow passage in between. We start with configuration space samples generated by the PRM planner. Then, we split the samples into two classes, according to whether they are connectable to the goal. In this case, the blue square points are the samples connectable to the goal, and the red cross points are the other samples. With these two classes of samples, we learn a manifold as a classifier. We use support vector machine with RBF kernel to learn the manifold. The two classes of nodes from disconnected components of the planning graph must connect with each other to form a path. Since the manifold as the classifier decision boundary separates the two classes, any valid path must cross the manifold, and more precisely, a collision-free configuration on the manifold. To find such configuration, we sample points on the manifold and then save the collision-free configurations. Then, we add the collision-free sample to the PRM planning graph, and this iteration continues. Here is a complete run of the algorithm in this 2D scene. The manifold is trained using the planning graph, the collision-free samples on the manifold are found, and these samples are added back to the planning graph. This iteration continues until we find the path. Next are the experiments. For experiments, we set up 4 scenes. In the 6-DOF and 7-DOF manipulator scene, the arm needs to go through a narrow space to reach the goal position. We also have a multi-robot scene where the 3-point robots needs to maintain line of sight while traversing to the goal. In the last scene, a twisted 3D object needs to go from one side of the wall to the other side through a small open window. Here, the videos show valid paths for the 4 scenes generated by our SDCL planner. We compare our algorithm with available planners in OMPL that are either widely used or offer competitive runtime. These graphs are showing mean and standard deviation results for the 4 scenes. We are only showing part of the more competitive planners' results. More statistics can be found in the paper. SDCL produces 1 order of magnitude speedup in the 6-DOF and 7-DOF manipulator scene. SDCL is also the fastest in the 3D free body scene. In the multi-robot scene, SDCL is slightly slower than the best baseline planner by a few seconds. We also test the change in runtime for varying levels of difficulty in the 7-DOF scene. We make the scene easier or harder by changing the distance between obstacles in the scene. SDCL has less runtime increase when the problem becomes harder. This indicates that sampling with SDCL is robust in revealing narrow passages, even when the problem becomes more difficult. To conclude, we presented a configuration space learning algorithm as DCL. This algorithm couples with PRM to improve motion planning in narrow passages. We evaluated the algorithm performance on 4 scenes, including a 3D free body scene, 2 serial manipulator scenes, and a multi-robot navigation scene. The algorithm is very effective for solving the manipulator narrow passage problems. The biggest limitation of this algorithm is that it currently only applies to kinematic motion planning problems. Thanks for watching, and feel free to email me if you have any questions.